Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 587, Erect the fence. This is a fascinating computational geometry problem that challenges us to find the convex hull of a set of points, which is the smallest convex polygon that can enclose all the given points. Let's dive in and explore the solution step by step. In this problem, we are tasked with finding the convex hull of a given set of points in a 2D plane. A convex hull is the smallest convex polygon that can enclose all the given points. Imagine stretching a rubber band around these points. The shape it forms is the convex hull. Our goal is to determine which points lie on the boundary of this polygon and return them in counterclockwise order. The input is a list of points, each represented as a pair of integers, x, y. The list can contain anywhere from 1 to 3,000 points. The output will be a subset of these input points, specifically those that form the vertices of the convex hull, returned in counterclockwise order. If there are multiple valid solutions, any order satisfying the rules of a convex hull is acceptable. Let's consider an example to make this clearer. In the first example, we are given the input points 1 1, 2 2, 2 0, 2 4, 3 3, 4 2. The convex hull of these points forms a polygon that encloses all the points. The vertices of this polygon are returned as 1 1, 2 0, 4 2, 3 3, 2 4, listed in counterclockwise order. Moving on to the second example, the input points are 1 2, 2 2, 4 2. Here, all the points are collinear, meaning they lie on a straight line. In such cases, the convex hull is simply the line segment connecting the first and last points, so the output is 1 2, 2 2, 4 2. This highlights that when all the points lie on a line, the convex hull includes all of them in order. The problem includes a few constraints and edge cases to keep in mind. First, the number of points ranges from 1 to 3,000, and each point is represented as x, y, with coordinates between -10⁻4 and 10⁻4. All the input points are guaranteed to be unique, and a valid convex hull is always guaranteed to exist. For edge cases, if there is only one point, the convex hull is just that single point. If all the points are collinear, the convex hull is the straight line segment formed by the first and last points. Additionally, any points that lie on the boundary of the convex hull must be included in the result. To solve this problem, you can use algorithms like Jarvis-March, also known as the gift wrapping algorithm, or Graham's scan. Jarvis-March iteratively identifies the outermost points to construct the convex hull in O, n*h, time, where n is the total number of points and h is the number of points on the hull. Graham's scan, on the other hand, sorts the points and uses a stack-based approach to construct the convex hull in O, n log n, time. Both algorithms rely on determining the orientation of points, whether they form a clockwise, counterclockwise, or collinear arrangement, to construct the hull. To solve the problem of erecting the fence, our goal is to determine the convex hull, which is the smallest convex polygon that can completely enclose all the given points. Several approaches can be used to achieve this. The brute force approach, while simple to understand, involves checking all possible subsets of points and verifying if each subset forms part of the convex hull. This is done by ensuring that all other points lie on one side of the line formed by any two candidate points. However, this method is computationally expensive, with a cubic time complexity of O, n cubed, making it impractical for large datasets. A more efficient option is Graham's scan algorithm, which utilizes sorting the points based on their polar angle relative to a reference point, often the lowest or leftmost point. By iterating through the sorted points and maintaining a counterclockwise order using a stack, we can construct the convex hull efficiently. This approach has a time complexity of O, n log n, primarily due to the sorting step, and is a significant improvement over brute force. Another technique is the Jarvis-March algorithm, also known as the gift wrapping method. This is a greedy algorithm that starts with the leftmost point and selects subsequent points in a counterclockwise order by finding the most left turning point. The process continues until the algorithm returns to the starting point, effectively wrapping the convex hull. Its complexity is O, nh, where h is the number of points in the hull, making it efficient for datasets where the number of hull points is much smaller than the total number of points. Finally, we have the monotone chain algorithm, also called Andrews' algorithm. This method is a variation of Graham's scan but uses a lexicographical sort of the points by x-coordinate, breaking ties with the y-coordinate. After sorting, the upper and lower hulls are built separately using a stack, ensuring counterclockwise orientation throughout. The final convex hull is obtained by combining these two hulls. Like Graham's scan, monotone chain has a time complexity of O(n log n), but its simplified implementation makes it an attractive choice. For this problem, we've chosen the monotone chain algorithm as the most suitable strategy. Its time complexity of O(n log n) is optimal for the typical input sizes encountered in this problem, and it is straightforward to implement. The lexicographical sorting of points simplifies the process of constructing the convex hull, while the separate construction of the upper and lower hulls ensures that the counterclockwise order is preserved without requiring backtracking. This method naturally handles edge cases, such as collinear points, by including all boundary points in the hull. When compared to Graham's scan, monotone chain avoids the complexity of calculating polar angles, making it less prone to implementation errors. Additionally, it outperforms Jarvis-Marchand scenarios where the number of hull points is close to the total number of points, making it a robust choice for a wide range of input sizes. When weighing the trade-offs between these approaches, the brute force method is clearly too slow for practical use due to its O(n)³ complexity. Graham's scan offers good performance at O(n log n), but the need to carefully sort points by polar angle adds an extra layer of complexity. Jarvis-March is simpler conceptually but becomes inefficient for large datasets with many hull points, as its complexity of O(n)h scales poorly when h approaches n. The monotone chain algorithm, on the other hand, strikes an excellent balance between simplicity and efficiency. By leveraging efficient sorting and a straightforward construction process, it combines the best aspects of Graham's scan while avoiding its downsides. It is also robust in handling edge cases like collinear points. For these reasons, monotone chain stands out as the optimal choice for this problem, offering reliable performance and ease of implementation. To construct the convex hull, which represents the smallest boundary enclosing a set of points, we rely on Graham's scan algorithm. This method is efficient, operating at O(n log n) time complexity. The process starts with input validation. If there are fewer than 4 points, we can directly return the input as the convex hull, since all given points will naturally form the boundary. This initial step helps us handle simple cases like a single point or multiple points in a straight line. Next, we need to determine the starting point, which serves as the anchor for the entire algorithm. To do this, we identify the point with the lowest y-coordinate. If there's a tie, or multiple points share the same y-value, we select the one with the smallest x-coordinate. This ensures consistency, and it's guaranteed that this starting point will always lie on the convex hull. With this anchor set, we can now prepare the points for processing. The next step involves sorting the points based on their polar angle relative to the starting point. The polar angle can be calculated using the arctangent function, and this provides a way to organize the points in counterclockwise order. If 2 points happen to have the same polar angle, the one closer to the starting point is placed first. This arrangement ensures we can process points sequentially to form the convex hull correctly. Once the sorting is complete, we initialize the convex hull with the first 3 points from the sorted list. These points form the initial boundary. To manage the convex hull dynamically, we use a stack, which allows us to efficiently add or remove points as needed. With the stack prepared, we begin iterating through the remaining points. For each point, we check whether adding it would maintain the convex shape. If the last 3 points in the stack form a non-left turn, the middle point is removed. This decision is based on the cross product of the vectors formed by these points, which reveals the orientation. We then push the current point onto the stack, ensuring the hull remains valid. As we iterate, we also account for collinear points, ensuring that all points on the boundary are included. This is particularly important for edge cases, where collinear points could otherwise be missed. Once all points have been processed, the stack contains the complete set of points forming the convex hull. These points, arranged in counterclockwise order, are returned as the final result. Several key insights make this algorithm robust. Sorting the points by their polar angle is critical for processing them in the correct sequence. The cross product is a fundamental operation, as it allows us to determine the orientation of 3 points clockwise, counterclockwise, or collinear. Additionally, the stack provides an efficient way to dynamically construct the hull by adding or removing points as needed. Lastly, special cases like collinear points and degenerate configurations, such as all points lying on a straight line, are handled carefully to ensure correctness in every scenario. The algorithm relies on two primary data structures, a list and a stack. The list is used to store both the input points and the sorted points, while the stack is used to keep track of the current convex hull during the iterative process. This stack is crucial for efficiently adding and removing points as the hull is constructed. In terms of complexity, the sorting step dominates with a time complexity of O, n log n, while the iterative hull construction takes O, n. This gives the overall algorithm a time complexity of O, n log n. The space complexity is O, n, accounting for the stack and sorted list. Several edge cases must be considered. When all points are collinear, the algorithm ensures that every boundary point is included. Duplicate points are ignored during sorting to avoid unnecessary processing. If the input size is very small, with fewer than 4 points, the algorithm simply returns the input. Lastly, when multiple points share the same polar angle, the algorithm prioritizes the closer points first, maintaining correctness. These considerations make the algorithm robust across a wide range of scenarios. This implementation solves the problem of constructing the convex hull of a set of points using the monotone chain algorithm, a variant of Graham's scan. Here's a step-by-step explanation. #explanation. 1. Cross product for orientation. The cross function calculates the cross product to determine if 3 points make a left turn, right turn, or are collinear. This is critical for identifying points that should be part of the convex hull. 2. Sorting the points. The input points are sorted by their x-coordinates, and in case of ties, by their y-coordinates. This ensures that we process the points in a consistent order. 3. Constructing the lower hull. The algorithm iterates through the sorted points and builds the lower convex hull. Points that would result in a right turn, negative cross product, are removed from the hull using a while loop. 4. Constructing the upper hull. The algorithm iterates through the points in reverse order to build the upper convex hull. Again, points causing a right turn are excluded. 5. Combining the hulls. The lower and upper hulls are combined into a single list. The last point of each hull is omitted since it is repeated as the starting point of the other hull. 6. Handling edge cases. If the input contains fewer than 4 points, they are all part of the convex hull, as per the problem constraints. This solution ensures correctness and efficiency with a time complexity of O, n log n, due to the sorting step. The algorithm is robust and handles all edge cases, including collinear points and duplicate points. Here, we start by importing the necessary Java utilities and defining our solution class. Within this class, there's a helper method called cross that calculates the cross product of 3 points. The cross product is essential for determining the orientation of 3 points, which helps us decide whether a point should be included in the convex hull. Moving on to the outer trees method, we sort the input points first by their x-coordinates. If 2 points share the same x-coordinate, we then sort them by their y-coordinates. After sorting, we build the lower hull of the convex shape. By iterating through the sorted points, we use the cross method to check if the last 3 points form a right turn. If they do, we remove the middle point, as it's not part of the convex hull. This ensures that the lower hull is built correctly step by step, adding only necessary points. Next, we construct the upper hull by iterating through the points in reverse order. Similar to the lower hull, we use the cross method to identify and remove points that cause a right turn, ensuring only the outermost points are retained. After constructing both the lower and upper hulls, we combine them into a single set. Using a hash set allows us to automatically remove duplicate points, as some points may appear in both hulls. Finally, we return this set as a sorted list, containing all the points that form the boundary of the convex hull. This implementation ensures efficiency while handling edge cases like collinear points or duplicate coordinates, making it a robust solution to the problem. In this problem, we are tasked with finding the smallest convex polygon, also known as the convex hull, that encloses a given set of 2D points. This type of problem is a classic in computational geometry and can be effectively solved using the monotone chain algorithm, which is a variation of Graham's scan. The approach involves constructing the convex hull in two parts, the lower hull, which forms the bottom boundary of the polygon, and the upper hull, which forms the top boundary. A key mathematical concept used here is the cross product. The cross product helps us determine the orientation of 3 points, whether they form a counterclockwise turn, a clockwise turn, or are collinear. This orientation is crucial for deciding which points to include or exclude when building the hull. With this foundation, we can systematically construct the convex hull from the given points. Let's look at a simple example to understand the process step by step. Suppose the input points are 1, 1, 2, 2, 2, 0, 2, 4, 3, 3, 4, 2. The first step is to sort these points by their x-coordinates, and in the case of ties, by their y-coordinates. After sorting, the points become 1, 1, 2, 0, 2, 2, 2, 4, 3, 3, 4, 2. Next, we build the lower hull. We start with an empty list and add points one by one. After adding the first 2 points, 1, 1, and 2, 0, the list looks like 1, 1, 2, 0. However, when we try to add 2, 2, we calculate the cross product of the last 3 points, 1, 1, 2, 0, and 2, 2. A negative cross product indicates a clockwise turn, so we remove 2, 0, and then add 2, 2. Continuing in this manner, we add 2, 4, remove it when adding 3, 3, due to the cross product, and finally add 4, 2. The resulting lower hull is 1, 1, 2, 2, 3, 3, 4, 2. Now, we construct the upper hull. This process is similar to building the lower hull, but we iterate through the points in reverse order. Starting with an empty list, we add the points 4, 2, 3, 3, 2, 4, 2, 2, 2, 0, and 1, 1, 1 at a time. At each step, we calculate the cross product to ensure that the points included form a counterclockwise turn. After applying this process, the final upper hull is 4, 2, 2, 4, 1, 1. To get the complete convex hull, we combine the lower and upper hulls, ensuring there are no duplicate points. The result for this example is 1, 1, 2, 2, 3, 3, 4, 2, 2, 4. Additionally, for edge cases, such as when the input contains duplicate points, sorting and building the hulls in the same way ensures that duplicates are automatically removed. Consider a scenario where all points are collinear, such as 1, 1, 2, 2, 3, 3, 4, 4. In this case, after sorting, the points remain in their original order, 1, 1, 2, 2, 3, 3, 4, 4. When building the lower hull, all points are added since the cross product does not become negative at any step. The lower hull is 1, 1, 2, 2, 3, 3, 4, 4. Similarly, for the upper hull, the points are added in reverse order, resulting in 4, 4, 3, 3, 2, 2, 1, 1. However, for collinear points, only the endpoints are needed to represent the convex hull. Therefore, the final result is 1, 1, 4, 4. This highlights an important property of the algorithm. It naturally simplifies the output to include only the necessary points. To summarize, there are a few key insights to take away. The cross product is a fundamental tool for determining the orientation of 3 points, helping us decide whether to include or exclude a point from the hull. Sorting the points by their x-coordinates, and by y-coordinates for ties, ensures a consistent and deterministic order, which is critical for the monotone chain algorithm to work correctly. Additionally, handling duplicates by using sets or eliminating them during the sorting step guarantees a clean output. For the examples we've seen, the final convex hulls are as follows. Example 1 produces 1, 1, 2, 2, 3, 3, 4, 2, 2, 4. Example 2 gives 1, 1, 2, 0, 4, 2, 3, 3, 2, 4. And example 3 simplifies to 1, 1, 4, 4. With these insights, you can confidently apply this algorithm to solve the problem and handle various edge cases effectively. The monotone chain convex hull algorithm, used in solving the erect the fence problem, has several components contributing to its time complexity. First, we have the sorting step. Here, the points are sorted by their x-coordinates, and in the case of ties, by their y-coordinates. This sorting operation is the most computationally expensive part of the algorithm, taking n log n time. Next, when constructing the lower hull, we process each of the endpoints, possibly adding or removing them from the hull. While this might seem like it could be costly, each point is added and removed at most once, making the total time for the lower hull n. Similarly, for the upper hull, we reverse the points and repeat the same process. Again, since each point is processed at most twice, the upper hull construction also runs in n time. Together, these steps form the core of the algorithm's operation. Once both the lower and upper hulls are constructed, the algorithm combines them into a single list. This involves concatenating the two hulls and removing any duplicate points. Concatenation is a straightforward n operation, and removing duplicates using a set is also n. When we sum up all these steps, the sorting step remains the dominant factor. As a result, the overall time complexity of the algorithm is n log n. This holds true in the best, average, and worst-case scenarios, as sorting is always required regardless of the input configuration. The space complexity of this algorithm is influenced by both the input storage and the additional structures used during execution. First, the input list of points requires n space, as it simply stores the coordinates of all the given points. Next, we have the auxiliary lists for the lower and upper hulls. These lists store the points that form each respective hull. In the worst case, every point could be part of the convex hull, which means both the lower and upper lists could together require n space. Lastly, the algorithm uses a few temporary variables, such as those in the cross-product calculation, but these occupy a constant amount of memory, or O1. Altogether, the space required is determined by the input and the two hull lists. Combining the storage requirements, the total space complexity of the monotone chain algorithm is n. This is primarily due to the input points and the auxiliary lists for the hulls, with no significant additional overhead. Comparing this to a brute force approach gives us further insight. A naive solution would involve generating all subsets of the input points to check which ones form the convex hull. This approach has an exponential time complexity of 2 to the power of n, due to the sheer number of subsets, and it also requires 2 to the power of n space to store these subsets. In contrast, the monotone chain algorithm is far more optimized, reducing the time complexity to n log n, through sorting and efficient hull construction, and keeping the space complexity linear at n. To mathematically prove the big O complexity, we start with the sorting step, which dominates the time complexity. Sorting n points requires n log n time. For the lower and upper hulls, each point is processed at most twice, once when it's added and once when it's removed, resulting in n for each hull. Combining the two hulls and removing duplicates is a linear operation, n. Thus, the overall time complexity is n log n, as the sorting step overshadows the other linear components. On the space side, the input points and the auxiliary hull lists together require n space, with no extra overhead from recursion or other memory-intensive operations. This makes the total space complexity n, keeping the algorithm efficient in both time and memory usage. One of the most common mistakes when solving the erect the fence problem is misunderstanding the definition of a convex hull. Students sometimes try to include all points, even those inside the hull, in their output polygon. However, the convex hull consists only of the outermost boundary points, excluding any interior points. Including interior points produces incorrect results. Another frequent error is miscalculating the cross product, which is essential for determining the relative orientation of 3 points, whether they create a clockwise turn, counterclockwise turn, or are collinear. Any mistake here can lead to an invalid hull or missed points along the boundary. Finally, some implementations fail to account for collinear points that lie on the boundary of the convex hull. These points must be included to ensure the hull is complete and correct, so skipping them results in failing the problem's requirements. Another challenge arises from inefficient sorting or handling of ties when sorting points by their polar angles. Algorithms like Graham's scan rely heavily on this step, and any inefficiency can increase the overall time complexity or cause the algorithm to fail. Also, it's critical to manage edge cases like fewer than 3 points or duplicate points in the input. Neglecting these scenarios can lead to runtime errors or logically incorrect results. For example, when fewer than 3 points are given, the convex hull is simply the set of those points. Similarly, duplicate points need to be removed or handled explicitly to avoid redundant calculations. Geometry plays a central role in this problem, and many candidates struggle with understanding the geometric principles involved. It's important to clearly explain how the cross product determines orientation and why sorting points by polar angles is a key step in building the convex hull. Additionally, you should be familiar with algorithm trade-offs. For instance, Gram-Sken operates in O n log n, making it efficient for larger datasets, while Jarvis's March, with its O n squared complexity, is more straightforward but less scalable. Interviewers also value how well you handle edge cases. Demonstrating robust solutions for scenarios like collinear points, duplicate points, or small input sizes shows attention to detail. If asked, you might also discuss practical optimizations, such as leveraging computational geometry libraries, which are often used for solving problems like this in real-world applications. The concepts in this problem are closely related to several other LeetCode problems. For example, problem 149, max points on a line, involves similar geometric principles, particularly when calculating slopes and handling collinearity. Problem 850, rectangle area 2, and problem 391, perfect rectangle, are also geometry-based problems, focusing on boundary calculations and coverage. Finally, revisiting problem 587, erect the fence, within the context of these related challenges helps solidify your understanding of convex hulls and computational geometry. These problems together provide a broader perspective on how geometric algorithms can be applied across various scenarios. There are several alternative approaches to solving the convex hull problem, each with its own advantages and disadvantages. Gram-Sken, with a time complexity of O n log n, is efficient for larger datasets but requires careful implementation of sorting and stack operations. On the other hand, Jarvis's March, also known as the gift wrapping algorithm, is simpler to implement as it doesn't require sorting, but its nested loop structure results in an O n squared complexity, making it inefficient for larger inputs. Andrew's monotone chain is another O n log n algorithm, known for explicitly handling collinear points and being both efficient and widely used, though it's slightly more complex than Jarvis's March. Lastly, the quick hull algorithm adopts a divide-and-conquer strategy with an average case complexity of O n log n, but its worst case complexity can degrade to O n squared, making it less reliable for certain datasets. Understanding these trade-offs helps you choose the most suitable approach for different scenarios. Great job! We've just explored how to solve LeetCode problem number 587, erect the fence, by computing the convex hull of a set of points. We learned about the Jarvis March and Gram-Sken algorithms, their time complexities, and when to use them. Thank you for joining me on this problem-solving journey. Be sure to like, subscribe, and stay tuned for more exciting challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!